Hi, I'm Jackson Leffler, and this is my project on the sun and the heat and light it releases. So as this project is about the sun, we must first begin by talking about what the sun is. The sun is the closest star to our planet Earth, standing at around 93 million miles away. This is fairly close, as the next nearest star is Alpha Centauri, which stands 4.3 light years away from Earth. With the sun standing that far away, it must be very massive for it to still emit heat and light that touches our planet. Thankfully, this is the case, as the sun holds 99% of all mass in our solar system. As I said, the sun does provide heat to our planet, so it must be very hot. The surface of the sun is roughly 6,000 degrees Kelvin, and even hotter in the core. This, plus the size and mass of our star, qualifies it as a yellow dwarf star. This means it has a yellow color and is relatively young in its life cycle, and will become more massive and red as it gets older. You may ask yourself, if the sun is that far away, how may I feel its heat or see its light? Well, here's the reaction on how it is done. First off, the reaction that takes place within the sun is referred to as nuclear fusion. The goal of this reaction is to take smaller elements, such as hydrogen, and to fuse their nuclei into larger elements, such as helium. This sounds simple enough, but the environment needed for this reaction is very extreme. In order to get these two nuclei to fuse, there must be immense heat and pressure. The sun offers both of these. Due to the large amount of mass within the sun, the gravitational pull on itself to hold its mass in place is very strong. And with all this mass held, pressure begins to build as particles move around within the sun, causing friction and heat to build up within the core. This is what kicks off the nuclear fusion reaction chain within the sun. The specific type of nuclear fusion that goes on within the sun is proton-proton fusion. The first step in this reaction is for two positively charged protons to fuse together. While this seems simple enough, it is actually very complicated. This is due to the protons both having a positive charge and experiencing electric repulsion as two positively charged particles repel each other. The act of this repulsion is called the Coulomb barrier. To break this barrier, enough heat and pressure must be applied to the two protons to force them to get close enough to break that barrier and interact long enough to fuse and create a new atom. This brings us to step 2 of the proton-proton nuclear fission that takes place within the sun. Step 2 begins with the product that is formed between the two protons that have previously fused. The product of these two protons fusing is simply a proton and a neutron. This is done when one of the protons undergoes weak nuclear forces and turns into a neutron. Through this, two reagents are left, with one being the formation of deuterium. The other is formed through the transformation of one of the protons to the neutron. This transformation leaves us with a positron and an electron neutrino. This newly formed electron neutrino does not stick around long though. They leave the sun in about 2 seconds. These neutrinos then travel towards Earth, approximately taking 8 minutes to reach us. Once here, they simply pass through us and are absorbed by the Earth. Now that we understand the formation of deuterium and the release of an electron neutrino and a positron, we are now ready to move towards step 3 in the process of proton-proton nuclear fission within the sun. Step 3 in this process is actually very simple. Here, we take our newly formed deuterium and a proton within the sun and fuse them. Obviously, this is done under the same conditions as the first step in our fusion process of great heat and pressure. As stated, this immense heat and pressure is caused by the sun's gravitational pull on itself and its own matter. Now, with our deuterium and proton fused, we are now left with helium-3 and are ready to move on to step 4 in the proton-proton nuclear fusion process. Step 4 begins with our newly formed helium-3 atom from our deuterium-proton fusion in the last step. Therefore, we take one helium-3 atom and fuse it with another helium-3 atom. This again is done under the same heat and pressure as the other steps in the fusion reaction. While this is the case, the heat and pressure here must be much larger. This is due to more protons being within the fusion reaction, causing the Coulomb barrier to be greater, and the energy and pressure to break that barrier even higher. With this step completed, we are left with one alpha particle, and are ready for step 5 in the proton-proton nuclear fusion reaction. Step 5 begins with the newly formed alpha particle. As previously stated, when two helium-3 atoms are fused together, they form an alpha particle. When this reaction takes place and the alpha particle is formed, there is also one more reagent. This reagent is two separate protons. With these two separate protons released, they can begin another proton-proton fusion reaction. With this alpha particle form, this is where the proton-proton fusion reaction ends within the Sun. Although this is where the proton-proton fusion reaction ends within our Sun, it is not the end for most stars. Much larger stars, with greater pressure, more gravity, and more mass that can create more heat, can move past this step. This is done when alpha particles fuse with alpha particles to continue to create larger and larger atoms, and can be done over and over again. Some scientists say that some stars are so hot and so massive and have so much pressure due to their gravitational force that they can fuse much larger elements, such as iron. But as stated, our Sun simply stops with the creation of the alpha particle. With how the Sun creates its light and heat covered, we may now move on to what the Sun actually emits and what we interact with every day here on Earth as humans. When talking about the emissions from the Sun that we deal with every day, we must first look at everything that is emitted from the Sun. The Sun emits a various amount of wavelengths along the electromagnetic spectrum. The electromagnetic spectrum is a various wavelengths of light that travel through space at the speed of light. The particular wavelengths the Sun releases are as follows: X-rays, ultraviolet light, infrared light, visible light, and radio waves. While all of these are emitted, certain wavelengths are more prominent than others. The most prominent out of these 5 wavelengths are infrared light, ultraviolet light, and obviously visible light. Out of these 3 wavelengths, the most prominent is visible light. This is what we humans interact with every day as daylight, which illuminates our planet. We perceive this light as white light that is then split up into its own wavelengths and has us perceive our sky as blue. The second most prominent wavelength out of these 3 is infrared light. This is what we perceive as heat. While infrared light cannot be seen with our own eyes, we do have the technology to monitor it. The third and least prominent of these 3 is ultraviolet light. Similar to infrared light, we cannot see ultraviolet light. This does not mean that ultraviolet light, though, is not dangerous. Ultraviolet light is what causes skin cancer. With this being the case, we can now see that infrared light and visible light are the most important out of these 3 for our existence on this planet. In conclusion, we interact with this process and these emissions in various ways, as they are the main purpose for our existence on this planet. With this being said, we are now trying to harness more energy from our Sun. This is being done mostly through through solar panels and solar energy. This technology will bring us much cleaner energy for the future and save our planet, as we may observe this reaction for much longer. Thank you for your attention. This is Jackson Leffler with my presentation on the sun and the heat and light released. Reference page as 12th slide.